In this video, let's learn about a special probability distribution called the binomial distribution. To understand the binomial distribution, we can consider a situation like this. Suppose there is a ring throwing game and you can throw 5 rings. Each throw is independent. That means whether your first throw is successful will not affect your performance of the next throw. And the probability of success of each throw is 0.3. We let x be the number of successful throws in this game. Now the question is, what is the probability distribution of this random variable x? Before I show you the complete probability distribution of x, firstly let's consider one of the probabilities, the probability that x is equal to 2. If x is equal to 2, that means there are 2 successful throws out of the 5 throws like this. All of these probabilities are equal, and there are 5 C2 cases here. So this probability can be calculated in this way. For the first 2 throws to be a success and the last 3 throws to be a failure, the probability is equal to 0.3 squared times 0.7 cubed. Therefore, the probability that x is equal to 2 can be evaluated by this expression. From this pattern, we can see that in general, to find the probability that capital X is equal to small x, it is equal to 5cx times 0.3 to the power x times 0.7 to the power 5 minus x. And the possible values of x are 0, 1, 2, 3, 4, and 5. We can see that there is a binomial coefficient 5cx in this expression. If we add up all these probability values, then by the binomial theorem, we can see that it is really equal to 1. In probability theory, this kind of probability distributions is known as the binomial distribution. We can use this notation to represent that x follows the binomial distribution. These 2 numbers are the parameters in this binomial distribution. The first number represents the total number of trials, and the second number represents the probability of success of each trial. More generally, if there are n independent trials and the probability of success of each trial is p, then x will follow the binomial distribution with parameters n and p like this. For random variables, we are usually interested in their expectation and variance. Now for this binomial variable x following b and p, before we can calculate the expectation of x and the variance of x, first of all, let's consider the expectation and the variance in this special case. Suppose this time there is only one trial in this game. In this case, the probability distribution is simply like this. This time x can either be 0 or 1, and the respective probabilities are just 1 minus p and p. This simple probability distribution is called Bernoulli distribution, which is named after Swiss mathematician Jacob Bernoulli. We can use this notation to represent that x follows the Bernoulli distribution. For x following b1p, we can easily obtain the expectation of x and the variance of x like this. We can get that the expectation of x is equal to p and the variance of x is equal to p times 1 minus p. Now for the general case x following b and p, it is complicated to find the expectation of x and the variance of x directly. So we can use a trick like this. We can consider that x is the sum of n Bernoulli random variables x1, x2 to xn. In other words, we can consider x as the number of successes in n identical and independent Bernoulli trials. For the sum of random variables, we have the following properties of expectation and variance. It is true that the expectation of x plus y is equal to the expectation of x plus the expectation of y for any random variables x and y. And the variance of x plus y is equal to the variance of x plus variance of y if x and y are independent random variables. The proofs of these results are complicated, and they will be presented in another video. In this video, let's just apply these properties to handle the sum of random variables. If we consider the binomial variable x as the sum of n identical and independent Bernoulli variables, then the expectation of x is simply equal to the sum of the n expectations of the Bernoulli variables. So we can get that the expectation of x is equal to n times p. For the variance of x, it is equal to the sum of the n variances of the Bernoulli variables. So we can get that the variance of x is equal to n times p times 1 minus p. With such knowledge of binomial variables, let's take a look at this example and see how we can handle some real-life problems. In a test, there are 7 multiple-choice questions, each with 4 options. Now a student answers each question independently and randomly, and we let x be the number of questions correctly answered by the student. In part A, let's find the probability that there are more than 4 correctly answered questions. It is clear that x follows the binomial distribution with parameters n equals 7 and p equals 0.25. Then the required probability is just equal to the sum of these 3 binomial probabilities. So the answer is 0.0129, correct to 4 dp. In part B, the required probability is the probability that x is greater than or equal to 2. That means x can be 2, 3, 4, 5, 6, or 7. There are many cases, so in this case we better consider the complement law of probability. So it is equal to 1 minus the probability that x is equal to 0 or 1, like this. As a result, the required probability is equal to 0.5551, correct to 4 dp. Finally, in part C, if each correct answer can score 5 marks, we need to calculate the expected value and the standard deviation of the score obtained. Here we can treat this score as another random variable y. Then we know that y is equal to 5x. For the expectation of y and the variance of y, they can be easily calculated from the expectation of x and the variance of x. And for the expectation of x and the variance of x, they can be obtained from these formulas that we have just learned. So the expectation of y is equal to 5 times the expectation of x, and it is then equal to 8.75. And the variance of y is equal to 5 squared times the variance of x, so it is equal to 32.8125. For the standard deviation of y, we need to take the positive square root like this. Therefore, we can conclude that the required expected value is 8.75 marks, and the required standard deviation is 5.7282 marks, correct to 4 dp. This is how we can apply the concept of the binomial distribution in real-life situations.